Here's problem 3 from the worksheet that we were doing in class. A lot of people missed it. This is looking at a particular example of a parametric curve. Zippy is a bug, and his motion is described by x equals secant of t, y equals tangent of t. We looked at, above this, we looked at, for example, cosine t, sine t, and we discovered that made a circle. And that's not an accident. Cosine t and sine t are designed to trace out the unit circle. It's a major part of what we were doing last semester with the trig. And so you might think secant t and tangent t, well, that should have something to do with the circle still. But it's kind of surprising that it doesn't look like a circle in the end. And then I made this restriction, only go from minus pi over 2 to pi over 2, and this is going to be in radians. All this stuff should be in radians. And we're going to have to discover why I put that in there. So the first thing I was asking was just make a table of t values, and then plot the xy values, and of course label with the t values. Oh, I think I didn't put the labels on, but I'll talk about the labels. So I'm going to do that in MATLAB. So let's bring up that in the figure. So let's put in t equals minus 1.5, and then secant is 14.13, and tangent is negative, but a very similar value. And so it ends up being down here. Positive x, negative y. Remember, we don't use the minus 1.5 as the plot. We would put here a label, t equals minus 1.5, which I didn't do because it's kind of a pain to do that in MATLAB. It's not impossible, but it's a pain. Now, zoom, wow, a quarter of a second later, he is much closer to the origin at 3.2 and about minus 3. Minus 1 second, he's getting closer in, but he's not going quite as fast anymore. And then let's just go a few more. This didn't format the same way, but he's finally gotten to 0, 1, 0. That's when t equals 0. You just get secant of 0 is 1 and tangent of 0 is 0. So he was moving really fast, and now he's slowed down. You can tell by the way that the points are spaced because we used equal spaced t values. So we made sure to use equally spaced t values, then it's very easy to see where slow and fast is happening. Fast, and then slow. And then it's going to be symmetrical the other way. Secant is going to give exactly the same values, and tangent gives the opposite values. If you compare these, they're the same except for sine. These are exactly the same. So remember, these are the t's. These are x equals secant t. These are y equals tangent t. And so we get a curve. It looks kind of familiar. It looks like it might actually be, I don't know, maybe a parabola, or maybe, well, let's see. Let's fill in the lines. Wow, this is looking really straight. This is looking really straight in a very different direction. That certainly looks like a hyperbola. Okay. And so let's see what I ask. Well, let's see. We really should put an arrow on it. And we already talked about constant speed. Well, let's put the, just note that this is negative t equals 0, positive t. So the arrow would go from here to here. And then again, you want at least a few of these explicitly with the t values, like t equals 0, t equals minus 1.5, t equals plus 1.5. At least a few to get an idea of the time and when he was at any particular point. That's important for a parametric curve. Okay, why do we restrict it to minus pi over 2 to pi over 2? Well, let's see what happens if we don't. Let's go ahead and do, these are what happens if I go past pi over 2. Right at pi over 2, it does not exist. The secant of pi over 2 and the tangent of pi over 2, if you try to calculate them, they don't exist. You could divide by 0. So something's definitely going on that's weird there. If you go right past pi over 2, you actually end up here, and then here, 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 here. You get all these very similar values, except you just reflect it across the x-axis. Well, given that we were guessing this is a hyperbola, that's not a shock to get the rest of the hyperbola. But what's a little weird is this idea that you trace this out, then you get it does not exist for momentarily, and then you jump, sort of infinitely teleport over to here, and then trace out this curve. If you let t keep going, what it does is it traces out this, then this, then this, then this, then this infinitely, and it keeps infinitely teleporting from going way off to infinity over here, and then suddenly it reappears way off at infinity down here and comes up, then goes off to infinity this way, and then teleports back off to infinity here, and then retraces both branches of the hyperbola. So it's pretty weird, and it's definitely not something a physical particle could do. But it's a cool way to trace out this hyperbola using trig functions, which we thought were just about circles. So let me just show you why we can really be sure this is a hyperbola. So let's see. Actually, why is it a hyperbola? Well, we want to eliminate the parameter because we're not familiar with hyperbolas in terms of parametrization, but if we can eliminate the parameter here, well, we don't want to just solve for t in terms of x, t in terms of y, and do inverse trig functions. That's ugly. We want to find some relationship that just talks about secant t and tangent t, and that's where we have to go back into our memories and realize there was an identity. 1 plus tangent squared t, was equal to secant squared t. Or I'm going to put the secant and tangent on one side. Secant squared t minus tangent squared t. That's going to be equal 1. Oh, that's interesting. So if I have an x and y pair where x and y were created as the secant and the tangent respectively of the same number, then x is going to be secant t, y is going to be tangent t, and x squared minus y squared equals 1. That is the absolute standard hyperbola with center of the origin and the asymptotes being y equals plus or minus x, which is in fact what we're seeing here. It's exactly those asymptotes. And the vertices are going to be plus or minus 1 comma 0. So this is actually, honest to God, a hyperbola. And notice we had to do a little bit of funky stuff to get both branches because this is not a connected set. There's no way that some nice curve, a continuous curve, to use a little more official terminology, there's no way a continuous curve could actually trace out both branches. So it has to sort of do a funky infinite teleport every time it switches from branch to branch. But it's able to do that thanks to the beauty of secant and tangent.